This is lab 6, Faraday's Law. So the purpose of this lab was to observe a magnet falling through an aluminum tube and then record the time it takes to fall through. Then the main model involved was Faraday's Law, and we used this in a computational model which was based off the real-life observation. And then we compared them both together, so the computational model took 1.19 seconds to fall, where the experimental model took 1.24 seconds on average. So the main physics principles involved were the Biot-Savart law, Faraday's law, Newton's second law, Ohm's law, the magnetic force on the loop, and the time derivative of a magnetic flux on a dipole, as you can see all here. So, observations. So we saw that the magnet took longer to fall through the aluminum tube as it would fall if the tube wasn't there. And the results of the experimental model, well, it took an average of 1.244 seconds, whereas the computational model took 1.188 seconds. So the conditions of the experiment, first systems and surroundings. So the system is the magnet, which is like the magnetic dipole, and the surroundings are the earth and the aluminum foil tube. Initial conditions, so initially the magnet is considered at rest and it's only being affected by Earth's magnetic field. And then we're going to assume that air resistance on the fog magnet is negligible, and gravity and magnetic force from the aluminum tube are the only forces acting on the magnet. Details of the experiment. So first, using the magnetometer on a cell phone, we found the north pole of the magnet. Then we used the phone's camera to record us dropping a magnet through the tube 5 times. Then using the timestamps of the video, we were able to find the time it took each magnet to fall through the tube. So here is our data from 5 trials, and here's our average. And here are just the measurements of the tube, so like the length, the width, the innermost radius, the outermost radius, what we found mu to be, the mass of the magnet. So for the computational model, we used Python code, which calculates the magnetic force on the magnet, which counteracts gravity, and then it calculated the induced current over the full radius of the tube in order to then calculate the magnetic force on the magnet. All right, so here's the start of our model. Here are just the physical constants, and then here's us filling out the geometry of the tube. These are the parameters of the simulation, and then this creates the tube of aluminum foil as rings stacked along the y-axis. This section of code creates the bar magnet. Here are initial conditions. Here we're taking in mu and r to find a magnetic flux. Here's the simulation loop. This is finding the gravitational force on the magnet, and then this is calculating d flux over dt. And then here's the last step where we apply Newton's second law and we find velocity versus time. And finally, here is our graph, and this is the time it took, and this is like a picture representation of what happened. All right, so choice of model. Well, because air resistance was likely negligible, there are no big discrepancies between the two possible models, and this is why the times are so close. Like 1.244 is pretty close to 1.188. The sources of error, though, could be an incorrect calculation of the magnetic dipole moment, and also another source of error could be human error in calculating the time it takes for the magnet to fall through the tube. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, if the resistivity of the conductor was reduced to zero, the induced current in the tube would be a lot greater. This means the magnetic force acting on the magnet would be bigger and it would slow it down even more. Could possibly negate the effects of gravity. What if you cut slots in the tube? How would this affect the ring currents in the model? If you put slots in the tube, then the induced current would be weaker, and this means that the magnetic piece would fall through the tube much faster. Thank you.